Remember, electricity is dangerous. Always make sure you're properly trained before working with electricity and electrical equipment. This is an IDEC FT2J. It's a PLC and an HMI combined into one compact, yet powerful device. Today, I'm going to use it to walk you through the core fundamentals of PLC control, step by step. In this video, we'll start by looking at the FT2J hardware, its inputs, outputs, and built-in HMI, and talk about the advantages of using a controller like this. Then we'll move into basic ladder logic, including normally open and normally closed contacts, coils, timers, and counters. After that, we'll build an HMI screen and finish with a simple control example using the IDEC FT2J. We are using IDEC PLC model number FT2J 7U22 SCFB. This particular model has 10 discrete, or digital, inputs that operate on 24 volts DC, and they can be wired as either syncing or sourcing. In addition, it has 4 more inputs that can be configured as either analog or digital, depending on your application. When used as analog inputs, they support 4 to 20 milliamps or 0 to 10 volts. If configured as digital inputs, they operate on 24 volts DC. On the output side, this PLC has 6 24-volt DC digital sourcing outputs, along with 2 analog outputs that can be configured for either 0 to 10 volts DC or 4 to 20 milliamps. The built-in HMI features a 7-inch display with an 800 by 400 pixel resolution. The FT2J has many more features and capabilities, but those are beyond the scope of this video. If you'd like to learn more about them, I've added a link in the description. So what are the advantages of the IDEC FT2J? Combining the PLC and HMI into one unit saves panel space and simplifies wiring. You don't need to purchase or integrate a separate HMI, which reduces cost and complexity. The programming environment is beginner-friendly, yet still powerful. It also supports Modbus and other communication protocols, so you can scale when needed. Overall, it's a cost-effective alternative to traditional PLC and HMI setups. The drawings I have been showing here are manufacturer reference drawings for learning purposes. In an actual project, you should always create your own complete control drawings specific to the application. I've added a couple of links in the description to help you create free drawings for the project you're working on. So how do we program this PLC? That is coming up next. For this programming example, I'm going to use a simple motor control circuit. A motor starter uses what's called a latching circuit, which keeps the starter energized even after the start button is released. This is done using a normally open auxiliary contact wired in parallel with the start push button. When the start button is pressed, the motor starter coil energizes and the auxiliary contact closes. That contact then holds the circuit on after the start button is released. The motor remains energized until a stop condition occurs. This can be pressing the stop button, which is wired in series, or an overload contact opening and removing power from the circuit. Keep in mind, this is a traditional relay ladder logic circuit using 120-volt control power. In our PLC application, the control voltage is 24 volts DC, so the output will be 24 volts DC instead. For the start and stop functions, we're going to program the HMI and use on-screen buttons instead of physical switches. For the M1 starter, which is a physical motor starter, we'll use output Q0 on the PLC. This output will energize the motor starter. Now for the M1 auxiliary contact, which comes from the motor starter, we'll use input I1 on the PLC. For the overload contact, we have a few options. Since the overload is already part of the motor starter, when it trips it opens the overload contact and de-energizes the starter coil, stopping the motor. Because of that, we do not have to use the overload contact in the PLC motor control logic. Another option is to bring the overload contact into the PLC as an input and use it for alarm logic. If the overload trips and the contact opens, the PLC can generate an alarm indicating the motor is in an overload condition. A third option is to use the overload contact as redundancy by including it in the PLC motor control ladder logic. In this example, I'm going to use the overload contact in the logic as a redundant contact. Now let's look at the programming software. Here I have the FT2J ladder logic software open. This is where you create your control program using basic ladder instructions like contacts, timers, and counters. The software also gives you access to more advanced instructions when your application requires them. On the right side, you can easily select and assign your inputs and outputs, making it simple to map the program to the actual PLC hardware. Overall, the software is very user-friendly and well-suited for both beginners and experienced users. Now, I'm going to show you the HMI software. This is where you select and place objects like push buttons and pilot lights, and then set the parameters that define their function and purpose. The library includes many options, such as charts, alarm lists, and alarm logs. The software is very versatile, and it allows you to customize the look and layout of the HMI to suit the application. Now let's start programming. Let's start with the HMI programming for the start and stop buttons, along with a pilot light for the motor. First, we select a push button from the library, place it on the screen, and then set its parameters. We configure it as a momentary switch and assign it to internal relay M0. This step is optional, but in the registration tab you can add a description to indicate what the switch is used for. That description will appear directly on the push button on the HMI. We can also use a text box to add a label above it, indicating that it's the start button. For the stop button, we follow the same process. This time, we choose a red push button and assign it to internal relay M1. Next, we'll add a pilot light from the drop-down to indicate when the motor is running. Since the motor output is Q0, we'll set the pilot light address to Q0. When the motor is running, the pilot light will turn on. Let's go back to the ladder programming software and start writing the program. First, we need a normally open start contact for the motor, and in the HMI program we assigned it to M0. We need to use the same address in the ladder logic for it to work. In the same manner, we'll add the stop switch, but this time it will be a normally closed contact, because when the button is pressed we want it to open the circuit. In the HMI, we assign this switch to M1. Next, we'll assign the motor output in the ladder program. This output represents the motor starter, and we've addressed it as Q0. Since the start and stop buttons are momentary, we need a holding contact. Normally, this would come from an auxiliary contact on the motor starter. Since we're not using a physical starter here, I'm going to use the Q0 output contact as the holding circuit. Just remember, When you're working with an actual motor starter, you should always use the starter's auxiliary contact instead. Now let's simulate the program and make sure it works. When we click the Start button, the output Q0 turns on and stays on. That tells us the program is working correctly. Now let's add the overload protection, which we've addressed as I0. Since we don't have a real overload contact connected, we'll use it as a normally closed contact so it stays on. In a real application, the overload contact from the starter would be programmed as a normally open contact because it opens when an overload occurs. Next, I'm going to add a timer and a counter to this program, then download it to the PLC and watch it run. Now, when the motor is running, I'm going to add a timer so the motor only runs for 10 seconds. This isn't something you'd normally do in a real application, but for this video, it's a simple way to demonstrate how a timer works. We'll use a normally open contact addressed to Q0, which represents the motor. Then we'll add a timer with a preset value of 10 seconds, followed by an internal coil addressed as M2. When the motor is running, the timer starts, and once it reaches the preset value, it energizes M2. Now I'm going to use M2 as a normally closed contact in the motor start rung. When the timer energizes M2, that contact opens and the motor drops out. Next, I'll set up a counter so that each time the motor runs, the counter increments. To do this, I'll use the M2 contact, which indicates that the timer has reached its preset value. This allows the counter to track how many times the motor has completed a run cycle. I'll also add a reset button on the HMI to clear the counter. For that, I'll assign an internal contact addressed as M3 to reset the counter. Now I'm going to add an internal relay, M4, that turns on when the counter reaches its preset value of 10. This means M4 energizes after the motor has completed 10 consecutive run cycles, with each cycle running for 10 seconds. Now let's go back to the HMI program and add a pilot light to indicate when the count has been reached, a counter reset button, and a display to show the real-time counter value. First, we'll add a pilot light and assign it to M4. This light will illuminate when the counter reaches its preset value. Next, I'll add a momentary reset button to clear the counter. This button will be used whenever we want to reset the count back to 0, and it's assigned to internal relay M3. Now I'll add a numerical display to show the counter value, indicating how many times the motor has run. To do this, we'll select a numerical display from the data display options, and for the display address, we'll use the CC000 register, which holds the actual counter value. Now we're ready to download the program. To download the program, we connect the Ethernet cable, set the IP address, and click Download. That's it. Now let's see how the program works. When we press Start, the motor pilot light turns on and the motor runs for 10 seconds. After 10 seconds, the motor shuts down and the counter increments by 1. Each time we start the motor, it runs for 10 seconds and the counter continues to count up. Once the counter reaches 10, the count reached pilot light turns on and we can reset the counter if needed. In this video, we walk through a complete PLC and HMI example using the IDEC FT2J, from inputs and outputs to basic ladder logic timers, counters, and HMI programming. The goal wasn't to build a perfect machine, but to understand how these core concepts work together. If this helped you better understand PLC control and HMI integration, give the video a like and consider subscribing for more practical, real-world PLC and electrical training. I'll see you in the next one.